Okay, good morning. What I wanted to go through quickly before we get into the specifics of each of the different GMPs and the proponent experts is to sort of focus on a couple of plots of comparisons and certain issues that sort of Norm mentioned before, and that hopefully the directed questions toward the proponent experts will help get a better understanding and resolution of. So if I go back and I start and I'm using the same 14 GMPEs that we presented yesterday, so it's the same suite of ground motion models. And I'm going to look first at some deterministic scenario spectra for Diablo Canyon and then for PV-NGS. And this plot is showing, again, very similar to what I had shown yesterday. On the top, you've got a log-log plot of median ground motions. On the bottom, it's a log-linear plot. This is for a characteristic event on the Haasgry fault. So we've got a magnitude 7.1. It's a vertical strike slip fault. It's at a rupture distance of about 5 kilometers from the plant. We put the top of the rupture at the surface because it's a surface rupturing fault trace. The depth has been associated to be 8 kilometers, and again, these are for VS of 760. So there are some things that we sort of talked about yesterday, but you can see as you get out at the longer periods or the shorter frequencies, you get a larger spread. So at 1 second here, you're seeing a bigger spread of the GMPEs. Other specifics to note is, again, this is the Bindi model, which is low at the high frequency range down here. And you've also got some models. This is the Camel and Bezonia, which seems to be a little bit more enriched in the high frequency range relative to the other models. But in general, there's a pretty good agreement, at least in this plot, for these models. If we go next to the shoreline fault, which is the close rupturing fault, it's a vertical strike slip fault again. It's a magnitude 6.5 that I'm showing. And again, this is at a distance a little bit less than a kilometer from the plant, 0.6. You can see that we're starting to see a bigger divergence in the models. So if you look at here, this is again the Bindi plot, the Bindi curve, which is coming down low in the high frequency and intermediate frequency range. This curve out here is actually the Zhao model, which is showing quite an increase relative to the other models. And then this curve coming down here is the ASB, the Akar et al. Model. So this is showing the difference as you go into sort of an intermediate magnitude, but you're going into close distances. If we then go next to the two reverse fault mechanism sources, we've got the Los Osos fault, given at a magnitude 6.8 for this plot. Again, this is a reverse dipping fault with the plant being located on the hanging wall. It's at a rupture distance of about 7.6. So because it's on the hanging wall, your JB distance would be 0. We've used the same hypocenter depth of 8 kilometers and again 760. What you can see now is we're starting to get a bigger spread on these models. You can see there's quite a bit of range here now, and that sort of has to do with the fact that some of these models include a hanging wall term, some of them don't. And so this is sort of the distribution that we're seeing, and Bob Youngs will talk a little bit later this morning on sort of the epistemic uncertainty and whether or not our current models are capturing the CBR, the TDI. If we look now, find the last one, the San Luis Bay fault, again, it's another reverse dipping fault. It's a little bit smaller magnitude for this comparison plot that I'm showing. So I've used a 6.3 on the reverse fault. Again, this is a dipping fault that goes under the plant. So we're on the hanging wall. The dip is about 50 degrees, and we've got a very short rupture distance. So again, this is a little bit closer, but smaller magnitude than the Los Osos in the previous plot. And you can get a very similar conclusion in the sense you get a larger spread here in the ground motion prediction equations. Again, this is the Zhao model coming out high. This is the Akar et al. Model coming out low at the longer periods of lower frequencies. And at the high frequencies, this is the Bindi model coming through there. If we now look at two scenario events for the Palo Verde plant in Arizona, the one I'm showing here is for a normal event, so it's a magnitude 6.5 on a normal fault. We're, in this case, at a distance of about 15 kilometers on the footwall side, so we're not over this surface projection of this fault. We have a dip of 45 and the same parameters that we'd used before for the other cases. You can see there's a similar type of range in ground motion models coming through here. And this one, the high one here, is the Grazier and Kalkin model, which is coming out higher than the rest of them. And this is the Zhao model again, which is coming out a little bit higher as you get out to the longer periods or lower frequencies. And then this is very similar to some of the plots we had shown yesterday and it's been discussed. This is for the larger magnitude strike slip event at 220 kilometers. So this is a 7.5. You get a very similar plot if you were to bump this up to a magnitude 8, like Norman just mentioned. And it's very similar to the plot I showed yesterday, which was a magnitude 8 at 200 kilometers. you can start to see now there is quite a big range here in the ground motion models as you get out to these large magnitude to large distances. And so this is something that will probably be investigated more, obviously, and hopefully the proponents will be able to discuss sort of the applicability and the use of their model and what went into developing sort of these median predictions for these curves. Now I want to go through and talk about some specific features of the curves or of the models. And so I'll go through a series of different cases where I'm comparing specific aspects of each model. So what I'm showing here is this is the magnitude scaling. So on the bottom axis across here I have magnitude going from magnitude 5 up to magnitude 8.5. This is for a vertical strike slip fault at a distance of 30 kilometers. So that doesn't change. The only thing that changes is the magnitude. So the distance will remain the same for each of the cases, and I'm just increasing the magnitude as they go up. It's the same suite of curves here with the same color line types. And on the left, I've got the PGA scaling, and on the right, I've got the 1 Hertz scaling. So there are a couple of things that jump out here. One is this dash curve, which we've talked about quite a bit in the last day and a half or so, is a Bindi curve. They have a change in their magnitude scaling at 6.75, and as was mentioned yesterday, their largest event, they have one event above 6.75, it's a 6.9 event, and they don't account for anything above that because they don't have anything in their data set. And so this is, at the high frequency, why we were seeing such a big increase. As you go up to the larger magnitudes, their scaling is quite a bit different than the rest of the models, leading to a lot higher median ground motion predictions on their magnitudes, larger magnitudes. You can see though, however, for the 1 Hertz case, their fit and regression and their model is actually coming in sort of the center of the distribution as you get to the larger magnitudes. So if you remember back in my median plots, their high frequency points are coming out substantially higher than the rest of the curves or the rest of the models, but by the time you get out to say 1 Hertz, they were falling in the distribution of the other models. The next thing I wanted to look at was sort of for Diablo Canyon was sort of the short distance scaling and how the models behave as you come in very close. Because if you remember for the shoreline fault, we've got a distance of less than 1 kilometer. The Hausgry is about 5 kilometers. So how do the models behave as you get into near source distances? So what I'm plotting here is again another vertical magnitude 7 event. The depth to the top of the rupture is just a little bit below the surface. And I'm plotting these curves now, the same suite of GMPE curves, for PGA on the left and 1 Hertz on the right as a function of Rx distance. And so if you think of because it's a vertical strike slip fault, you know, Rx is just a horizontal distance. And the top of the fault is just a little bit down from the surface. So what you can see here for PGA, there's a pretty good agreement as you get in close here, except for, of course, the Bindi curve is coming in low. It may not be as easy to see at the PGA case, but you can see a little bit clearer out here at the 1 Hertz case. This curve that's flat and actually comes down and oversaturates a little bit is a Grazier and Kalkin model, and then it sort of has a slight increase and then drops off and falls down by the time you get out to about 15 or 20 or 30 kilometers. It's coming back down within the distribution of the models. The other thing to note here is that you see there's a tighter distribution of the models for PGA as there is to 1 second. And in addition, it may not be as easy to see, but the color-coded top 5 curves, which are the NGA West 2 models, are predicting lower ground motions at 1 Hertz relative to their 2008 versions. So those ground motions have come down a little bit. At PGA, it's not as clear, and the NGA 2 models are very similar to the NGA 08 models. Now I'll go through a series of looking at the hanging wall features of the models. And so what I'm showing here is this is for a reverse fault for a magnitude 6.7 earthquake. It's a dipping fault with a dip of 45. And I've got 2 versions of the plot. I've got a surface rupturing fault and I've got a buried fault. And so down below here you can see the cross section with the red fault plane. This one's coming all the way to the surface. This one's been pushed down to a depth of 6 kilometers for the top of the rupture. And I plotted sites here to this is the Rx distance, so I plotted sites here on the left-hand side. These would be the footwall sites, and these sites over here would be the hanging wall sites. There are a couple of features of the models that are clearly evident. Certain models are only defined as a function of JB distance. So as you go out over the surface projection of the fault, you know, that JB distance would be the same. It would be 0, and so you get a constant ground motion prediction of the median ground motion as you go across that. And then as you get beyond the extent of the surface projection, the models start to fall off. And looking at this, you can see there is a big range as you're over the hanging wall sites. So again, this would be the applicable cases for Diablo Canyon because you've got two reverse faults that you're sitting on top of on the hanging wall site. And you can see a little bit larger spread over the hanging wall sites as compared to, say, over the footwall sites. And it's a little bit better, a little bit smaller spread as you get over a buried fault as opposed to a surface rupturing fault. The other things to notice is that the Bindi model here and as well the BSAA model are a little bit low in this comparison for the surface fault, but by the time you put the fault down at 6 kilometers, because of the tighter clustering, they're actually coming in a little bit better with the distribution of the models. This is all for PGA. The next thing I was going to look at or sort of present is sort of put it out there for discussion that will go forward when the proponents get up here for their models is looking at the soil response. So what I've been showing yesterday and what I had shown most today so far is for a VS of 760, sort of a reference VS value. And I'm plotting here now, again, my favorite magnitude 7 for PGA. These are for two additional VS30 values. So 550 meters on the left and a real hard rock or typical California hard rock of 1100 meters per second on the right. What you can see is, besides the fact that the Bindi model is coming out low, is that as you move away from 760, you start to get a larger spread in the models. And so each of these models has their own way of handling the nonlinearity or the soil response. As I mentioned yesterday, two of the models are actually just binned by site categories. They're not as a function of VS30. But overall, you can see the 760 actually gives a better agreement between the models than if we were to run something for 1100 or something for 550. That was, the previous plot was for PGA, and this is for 1 hertz, the same type of situation where I've got 550, 760, 1100. You can see, as I mentioned before in some other plots, that the distribution of the models is larger for 1 hertz than it is for PGA. And again, in this plot, you can see at the 1 hertz case, you've got the Grazier and Calkin model, which is sort of oversaturating as you get into these shorter distances, and then is a little bit high out here relative to the other models and then drops off. And by the time you get out to about 30 or 40 kilometers, it's falling within the distribution of the other models. Now if we move to Palo Verde and the Arizona site and sort of some of the features of the models that would be applicable to that. This is looking at the sort of depth scaling. And so let me take a second to explain this. What I'm showing are results from a magnitude 6 earthquake. So it has a width of roughly 10 kilometers. And I'm looking at a horizontal distance of 10 kilometers, so a JB distance of 10 kilometers. It's a vertical fault. It's for PGA. I'm plotting this as a function of the depth to the top of rupture. And so basically right here at the 0 axis, what I'm saying is I've got this magnitude 6 earthquake with a width of 10 kilometers that's right at the surface. And then what I want to look at is I want to look at, well, what happens if I push that fault surface, the top of the fault surface, down in depth? And so this is looking at that depth of scaling, the depth to the top of the scaling. For the Camel and Berzonia model, of course, they want the hypocentral depth. And so what I do in these cases is I take the center of this 10-kilometer width fault and put the hypocenter at that depth. So for the first, at a surface rupturing, that would be basically at 5 kilometers. And then as I move the fault width down, it would shift it down accordingly. So what you can see here in this plot is, again, this is a suite of curves that are shown by the legend. The top is for strike-slip mechanism and the bottom is for normal. They're very similar. There are some features that are a little bit different based on the faulting mechanism. But the other thing to notice is that some of these models are perfectly flat across, and that's because they're a function of the JB distance, which doesn't change, or they won't have a function of the depth to the top of rupture. So again, that wouldn't cause any change in their ground motion predictions. But you can see you have a spread in the models. And the reasons that some of these models start to dive off is as you go to a deeper top of rupture, not only are you changing the top of rupture, but you're also changing the rupture distance because of the slant distance. You've got 10 kilometers on the horizontal distance, and then you've got the horizontal depth as well to get the rupture distance. So it's a trade-off between this depth to the top of rupture feature in their models and as well the increasing rupture distance. So this is something that will be applicable in the Arizona site in the sense of at what depth do you put these sort of normal faultings in the background zone around the plant. If I do the same type of hanging wall footwall comparisons, but now for normal faults for the Arizona site, again, it's a magnitude 6.7, dip of 45. On the left, I've got, for PGA, the surface rupturing normal fault, and on the right, I've got the buried normal fault with the depth of 6 kilometers to the top. You can see it's a very similar type of distribution of the models and features. In fact, you've got some flat parts over here for those that are defined by a function of JB distance. And as well, you get a little bit larger spread for the surface case than you do for the buried case. The next thing and the last thing I'll talk about is what to do about the large distance from the large magnitude. So even though I've only done this for magnitude 7 just to be similar to the previous plots, you get a very similar result, a little bit larger spread for the magnitude 8 cases. What I'm showing here are attenuation curves, median attenuation curves, out to a distance of 300 kilometers. For the different models, on the left, I've got PGA. Well, these are both for PGA, but let me explain a little bit of what I'm doing differently. On the left, I've got the 14 GMPE models. So those are the ones we've been looking at. Those are the ones we've been considering. You can notice out here as you get beyond 100 kilometers, there starts to become a larger spread in the ground motion models, and it starts to sort of flower out if you look at it that way. Now, for the NGA West 2 models, several of the models have published different attenuation features of their models, such that for different regions throughout the world, they'd have a different anelastic and geometrical attenuation as you get out to larger distances. And as well, not just the NGA West 2 models, but the Grazier and Kalkin model has a feature where you can enter a Q value, which affects the long period or long distance scaling. And so what I'm showing out here is not just the 14 models that we're showing on the left, but I've included now all these sort of regional variations of the NGA West models and 2 different Q models for the Grazier, the GK model. So the base case that I've been showing in all these cases is a Q of 150, and then I've used a Q of 75 and a Q of 300. So I didn't change the line types because I'm just looking at sort of the cloud of the curves or the distribution of the curves. And you can see now here, if you were to consider, say, for example, ASK has a Taiwan version, a China version, and a Japan version. BSAA has a China and Turkey version, an Italian and Japan version. Camel Bisogni has a Japan and a China version, and Cho and Young's have a Japan and Italy and a China version. If you throw all of those into the mix, this is now the distribution. And you can see now you're getting a wider distribution as you're getting out here to these larger distances. So you know, one of the questions I think that might be applicable, of course, for the Arizona site would be, you know, are these adjustments based on regional attenuations applicable to events from California that are being recorded in Arizona? And I think in looking at the empirical data from the Arizona stations recording California events, that'll be something that'll be looked into and be able to be better refined. And then just for completeness, this is the same set of plots, but this is now for 1 hertz. So again, on the left here, I've got the 14 sort of suite of the GMPEs, and then over here on the right, I've included all those variations, the regional variations. And for the most part, you can see that you're getting a wider spread as you get out here to beyond 100 kilometers. Less than 100 kilometers, of course, it doesn't have a big impact because these are sort of regional attenuation features, and they're not expected and they're not modeled to sort of impact the shorter distances. And then finally, I guess my last plot of the morning before we get into the proponent expert discussion is to look at the sigma, because as we all know, that it's not just the median ground motions that are important in the hazard, but it's also the sigma values. And Linda Alatak will talk about this more, I think, tomorrow, breaking down the sigma. But basically what I'm showing here now is for a magnitude 7 at 10 kilometers. On the left-hand plot, this is the total sigma for all of the 14 models. And then on the right-hand plot at the top, this is the phi term and this is the tau term. So this is breaking out the sigma into the 2 terms. Again, there were 2 models, the Idris and the GK, that don't have published versions of the phi and the tau terms. They just have the total sigma. So you can see that when you break this out, if you look at the tau terms, there's a fairly consistent range. There are some peaks and valleys for some of the models. And as well, the Bindi model, as you get less than, say, about 5 or 6 hertz, it has quite a high value in the tau term. And as well, in sort of a trade-off, if you get higher than that, you have a high phi term such that their total sigma term is high. The other thing to note is that these 3 high sigma value models, in the high frequencies at least, are being contributed, are from the non-NGA models. If you look at the NGA West 2 models, they tend to be sort of down here in the center of the distribution. And so I think one of the things that will be discussed going forward for each of the proponent experts is sort of what went into developing their phi and their tau and their sigma models, and so that that can be used to help decide and discover and determine which way we want to go forward in developing the sigma model as well. Any questions? Hi.
This is Sinan Akkar, okay, from METU. You have been testing or evaluating Bindi et al. 2011.
Yes.
But I mean, I'm sure that you are aware of the most recent model of Bindi et al. 2013, and I believe that supersedes Bindi et al. 2011. It is again based on the European data set. You may consider the new Bindi et al. Model as well in your calculations.
Okay, that's a very good comment.
Testing. I think, I will try to address it in my presentation, but the lower, say, ASP estimations with respect to the NGA models, it could be because, I mean, always the European ground motion data set, I mean, the European data, gives a little bit lower values in terms of spectral ordinates. This could be one explanation. The other one is addressed by the lower values of, say, European data, ground motions. The other explanation could be the higher decay rate of the European ground motions, which is addressed by Scacera et al. 2008 paper, isn't it? So in that paper, they particularly indicated that the Italian data, the decay rate of Italian data is higher with respect to the Californian data. So this could be another reason of observing lower spectral ordinates at larger distances for European models.
Okay.
Thank you.
Thanks. Tom?
Tom Eaton here. For the Hosgri magnitude 7 simulation, if you go to the long period part and you looked at spectral displacement in zero distance, it should go to almost the fault slip for the Hosgri fault. And my question is, can you back out what those displacements are as a function of probabilities for whatever you're interested in? I mean, so ultimately, going through this exercise is, we do it all through magnitude, but it's all related to slip, and whatever number we come up with, we're making some statement about the probability of different slips. I'm curious what those numbers are.
We haven't done that yet, Tom. So what you're really saying is bring along almost a hazard curve for the surface slip to see if that's fitting with the hazard curve for your ground motion. Is that right?
This is a reality check.
Right.
So ultimately, again, the geologist goes out and sees a fault and is trying to say something about what might happen on the fault. And the reality will be some slip, and we want to make sure that after we run through the whole process, that our long period estimate is compatible with what was assumed about projection probabilities of slip.
Right. So we're going to try to do part of that with the slip generator part, where we look at those slip distributions and so what the surface slip is at the surface slip is compared to the ground motion. And I think what you're suggesting here is look at it even for the faults in the GMPEs of what is a surface slip hazard versus a ground motion hazard.
That's correct. So,
okay.
I mean, we don't want to be in the position where there's a 7-meter slip on the Hosgri fault. We see 5-meter displacements at Diablo, and it's not plausible in the probabilistic models.
Okay.
Ralph?
Ralph Archuleta from UCSB. Nick, two questions. One of them was that when you were showing the dipping faults and on the hanging wall, I recall seeing an earlier map in which basically Diablo Canyon, I don't remember the name of the fault that's to the north of Diablo Canyon, but basically Diablo Canyon was at the back side, just at the edge of the down dip extension of the fault. And so
Yeah, the Los Osos fault.
that's the Los Osos.
Yeah.
And is the other fault also, are you really sitting above the hanging wall or are you sitting at the edge?
You're sitting more above the hanging wall of the San Luis Bay fault because that runs just off the coast and dips to the northeast.
Okay.
There is a question of which one is the through-going fault and
Yeah.
which one cuts the other one off. And
Right.
so those are both being considered. So one could be thought of as a back thrust of the other fault.
Okay. That's what I was wondering about.
Yeah,
Yes.
so they're both sort of coming together and uplift, part of the uplift that the iris shows.
Okay. The second thing is with regard to the Palos Verdes, you mentioned a lot about the widespread, when you look at those distributions out there at 200 kilometers.
Mm-hmm.
But nonetheless, when you look at the PGA out there, you're looking at numbers that are under 0.1% or something like this. It's a very small number. So is that, it's one thing to talk about the widespread, but is the design that low? So that you have to worry about numbers that are, 0.1% G or something like that?
Well,
Or 1%?
these are median, but when you throw it into the hazard and run it all the hazard in 10 minus 4, 5, and 6, I think you're going to get numbers larger than, say, 1%. And so it is something that you need to consider.
Okay.
So it's not just the median, I threw that last plot in there, the sigma, but it's a combination of the both.
And the sigmas are in log-based 10 units, correct? Or are they
Natural
natural?
logs.
They're natural logs,
Yeah.
okay. Thank you.
We're just, with the high rates of earthquakes on those big California faults, to get to low probabilities, you have to go way up the tail of the ground motion distribution. That's why it's not negligible anymore. I think by the time you got to 10 to the minus 6, it was all driven by the local faults.
Correct.
Right. Melanie showed yesterday, then the contribution from these things goes away just for the reason you talked about.